In 4.4, we're going to look at something called concavity, inflection points, and then just general more on curve sketching. So let's draw draw on these two different pictures, your coordinate axis, and then basically a curve that opens like this. And it could be a parabola, it doesn't really have to be anything specific. And then a curve that opens down like that. So we're going to do two, just for a few lines, two descriptions of what's what. So the first description is that, and I'll draw it in a second, but for the left-hand side, if you look at tangent lines, the way it's drawn, all tangent lines are below the graph. So if you draw in tangent lines like this, and let's just pick a color here, and you draw on these tangent lines, you can see that they're all below the graph like this. Do another one here, right? It's all, it's not like going into the graph in any way. You could do a horizontal one. Okay, then so it's below everything, and then over here on this right hand side, all tangent lines are above the graph. I'll draw that verbiage here in a second. But you can see all these tangent lines this direction are above the whole curve, the whole graph. So here, in this case, all tangent lines are above the graph. And then specifically, we'll look at like on an interval, like A to B, for example. So if you're looking at from A to B, that's kind of what's going on. Let me put A inside just to make it easier on me. Okay, it doesn't really matter where A and B are, but so let's just consider it what's going on within that interval. So we'll call that interval I, and you can see that all tangent lines are above or below the graph respectively on that interval. And in the way I drew it, it's really on all reals. Of course, the graph is just open up. But I mean, a graph might do something else over here, so we don't know what's going on. But but generally, you talk about this on some interval. Now, what about the derivative? Consider the slope of this tangent line. This is a negative slope, and then you could have like another one like this. It's negative, but it's less steep, right? And then it's 0, and then positive derivatives, right? If you're looking at maybe just around points within the interval. So the next thing to describe this is that the derivative f prime is increasing. F prime is increasing, not f necessarily. F prime is increasing on the interval. Okay. Also, what we will have, and I'll show you this, f double prime is greater than 0 on I. That's what'll happen, and that'll be part of our definition. On the right-hand side, for that orientation, that picture, we have f prime is decreasing. On I, on the interval I. And in that case, we will see that f double prime, or we'll define it, or we'll show it to be less than 0 on I. So what that means then, this has a name. This is the concavity of the the statement. So of the pictures, the picture, the graph, whatever. So on the left-hand side, we call that concave up. Okay, so concave up, it's like it can hold water. Not necessarily, but that's what you could think of it as. Concave up means you can hold something above it like that. Okay. Concave down would be the upside down reverse of it. It's like holding a bowl upside down. So we call this concave down. So the concavity of a function on an interval is whether basically the definitions is f double prime is positive or negative. That's how it's defined, is really these two things. Whether the second derivative is positive or negative, we call it concave up or concave down. All right. So, and then let's define an inflection point. So when so this is less than and greater than. So what about at zero? What's that called? And I don't have a picture of that here, but it would look something like, I'll draw a picture in a second here. So the definition of inflection point is when it changes concavity. Okay. All right, so here's I'll just write it here. So definition an inflection point I'll just say for a graph of f is where the graph changes concavity. So, and occurs if f double prime is equal to 0 or f double prime does not exist. So they're critical points again, where f double prime is 0 or f double prime does not exist. We'll still call those critical values, and then you still have to test it to see if it actually changes concavity. One of the key graphs you want to keep in mind, there's actually, well, there's a lot, but two of them in particular, and I hesitate to write this here, but just write it down somewhere else. Consider x to the fourth, and consider x to like the fifth, because when you take first and second derivatives, you get different stuff going on, but they may or may not be. So you get at 0 in both cases, you get f prime is 0, you get f double prime is 0, y prime is 0, y double prime is 0 in both cases, and it doesn't necessarily do anything. So you have to test to see if concavity or it changes, or to see if the function has a max or min or something like that. So keep those in mind. I'm going to erase them now because I don't want to confuse the work. But those are the cases you keep in mind, and so investigate those. Actually, yeah, I need to show you other stuff. All right, so okay, so that's the definition of an inflection point. And I have another good graph here. In fact, I'll probably copy it over because I made it so nicely before. Well, let's see. So let's look at this example. Let's see, where is it? So this should help us kind of investigate what's going on. And this is just about concavity. So let's look at an example of concavity. We won't do max or mins right now. So if f of x is equal to x cubed plus x squared minus 5x minus 5. Determine intervals of concavity, or intervals f is concave up or concave down. Sometimes I've seen some books, they'll say like discuss concavity, but that's what they're asking. Determine intervals f is concave up or concave down. And indicate inflection points. Let's put that abbreviation up here so we know. So often it's IP for inflection points. Sometimes you'll reverse the order of the noun and verb, I guess is what it would be. I'm not sure. Or points of inflection. It doesn't matter. It's a description of the definition. Either direction is fine. Either, but I usually call them inflection points for some reason. I don't know why. All right, so you, just as before, you take the first and second derivative. What I had just thought of, though, is the examples we give initially are always usually just these polynomials. So polynomials are always nice and smooth. You should study again about basic shapes of polynomials. We know quadratics basically open up or open down. We know a cubic basically goes like that or goes like that. But it may have other dips and turns in it like that. So that could be the basic shape of it. Or maybe not. Maybe it just does that. It just depends on the situation. But you need to know your basic y cubed, x cubed kind of powers. And also what happens if you put a negative here. So if you put a negative, then the graph does that. If it's positive, then the graph does that. And you take a limit. So you need to know the basic concepts of all the parabolas. Okay, so start taking derivatives. F prime of x equal to 3x squared plus 2x minus 5. Now, if you set that equal to 0 and solve, then you'd be finding your local min and max, or your critical values. And then for a parabola, I can tell you it's probably going to be for a parabola. For a polynomial, it's often going to be max or mins. Sorry. This looks irrational. I can tell because of the 5 and the 3. Probably irrational. Anyway, but we're not doing that. We're doing it one step at a time. Next thing is take the second derivative, and I'm going across just because it's easier to show you all together here. So that's going to be 6x plus 2. All right, then you set that equal to 0 and solve. Divide by the 2, so you get 3x plus 1, so x is equal to just negative 1/3. Nice rational number. And so we want to investigate around negative 1/3. See, we're going to look at f double prime of x for x less than negative 1/3, and then x greater than negative 1/3. And we want to see what the concavity is. Does it change concavity around that point? So this is like the first derivative test where you have to check increasing, decreasing. All right, so that's what we're going to do, is look at increasing, decreasing of f double prime. So f double prime, and actually this should really be down here. So So I'm testing f double prime, and you can test a value, but you don't have to. I mean, you can. I could set this up how we've done in the past, where you test a specific value. So I'll just write it down, I guess. Test value. Okay, so f the test. So and then you have like the sign. So test value less than -1/3. Let's just test -10. Test value greater than -1/3. Well, easy when the test is always 0. So really what we're doing here then is the sign of f double prime. Okay, so is it greater than 0 or less than 0? So what's the sign? That's all we're really looking at. So we're now going to look at this. If you put in -10 times 6, well, that's negative, right? I mean, that's concave down. Okay, so this is negative. Okay, so then we know that implies it's basically concave down like that. And then at -1/3, it's 0. Okay, and then if you test 0, you get +2, so this is positive, it's concave up. So what that tells us here, therefore, -1/3 is an inflection point. And then the point is actually f of -1/3, but let's just leave it like that. And the intervals of concavity then would be what? Okay, so we would say f is concave up on negative infinity to -1/3. And then f is concave. I flipped that around, didn't I? Concave down on that interval. Okay, so less than 0 means concave down. And it's concave up. Okay, sorry about that. Okay, so it's concave down because of this, everything to the left of -1/3. So, I mean, I don't want to get too complicated here, but basically you're just looking at an interval number line, and you're testing at -1/3 here, and you're going to the left and right of that because that's where we know it changes sign. You only get one. There's only one to test here. All right, so then it's concave up everywhere else. So that's -1/3 and then approaching infinity. So the graph probably looks something like this, and this is just a sketch. I'll just make it look like a sketch. The graph does probably something like this. And then right at -1/3, right about here is where you can see it changes concavity from concave down. So this is basically implying it's down somehow, like in here. Okay, and then right at that point it changes to being up. Right in here, so that's kind of up. Okay, and that's not really what you use to show it, whether it like has water or not in it, but basically that's what it's looking like from being concave up to concave down. So this is an inflection point, which we will be finding as part of our process for curve sketching. So let's look at this graph, and I'm going to capture it because it's really nice looking, actually. So it's this one right here. Okay, so you can ignore the primes there for a second. I'm just going to capture the graph. because it looks really nice. Sometimes it's easier just for you to pause it and sketch that. And let's suppose you didn't see any of these right here right now. Okay, you didn't look at all those guys. We'll redo that right now. So let's just look at that graph for a second here. So do you know the graph's coming down like this, and then it curves back up? But right there, right here, you can see it changes its direction and orientation, right? So that looks like an inflection point. And then it's going like this, and then so I mean, the function's decreasing to here, and then it's increasing. But if you look at the slopes, it's always increasing all the way to that point. And then the function starts increasing. Then it starts decreasing. Okay, but you can see it by the kind of the orientation of the graph. This is kind of up, and this is down. Okay, and so the second derivative at 0 tells you this possible point. These are all critical values. They're possible points. And then this one goes up to here. Now that's a corner. So that is where we would have here f prime is a DNE. Now if f prime is a DNE, so is f double prime. That's also a DNE. And we'll get into that in particular, but they're both does not exist at that point right here. So it's a corner. Same goes for the cusp. Let me make this let's change that to a C4 and then C5. So I'm trying to show you, these are the nice smooth polynomial type stuff, but you also have these corners and cusps that are going to show up. So at this corner, you're going to get a DNE for both f prime and f double prime. But you still got to test concavity. And if you look at this, this is concave up, but here it changes to concave down, and it's still a DNE. Okay, so that is an inflection point right at C3. But then look at this graph. This graph goes, this is concave down, right? And then you have a cusp. As it changes at C4, is it still concave down or concave up? And those are still concave down. So this value here is also going to be a does not exist. Okay, and maybe I could point to those. Okay, so here and here are both DNEs for f double prime. One of them is an inflection point and one of them is not. Okay, so this is an inflection point. Just by the graph, I mean, it's good enough for now. That's an inflection point. This is an inflection point. Okay, and this is not an inflection point. And then we have another one here, an inflection point. So there's some questions that basically just say on what interval is it concave up, concave down. And so, and I'll put it in the intervals here what the derivative would be, second derivative would be. So here f double prime will be positive. Here f double prime will be negative. F double prime positive. F double prime negative. And still f double prime negative in between there. It's still concave down, and then f double prime positive, and then it goes concave up. Way over here. This is concave up. That's concave down. See that? See where that changes right there? So intervals of concavity, you would just state that in interval notation. And then the other thing you'll get is f double prime of C1 will be 0, and then etc. That's what I actually had you erase. You may still have it there, that's fine. And then here f double prime of C2 is equal to 0, f double prime of C3 is a DNE, does not exist. F double prime of C4 is another, does not exist. And then f double prime of C5, it would be equal to 0. So just like the first derivative test, you have to investigate around the point to see if you go from positive to negative or vice versa, from negative to positive. Okay, so that's all about inflection points. Let's look at what's called the second derivative test. So the second derivative test is, well, not unique, but it's only used for specific cases. So this is called the second derivative test. So I want to say this right up front because I don't want to, well, actually, it's on the intervals. So you got to be careful in this one. So you can use this when a function may not exist other place, different values, or f double prime or prime doesn't exist. But you got to look at the actual intervals. So I'll have to state the hypothesis as it should. So suppose f prime exists, that's critical that it exists, on the open interval from A to B. And C is in that open interval from A to B. Okay, and then assume f prime of C is equal to 0. Yeah, that's all I need. I have other stuff written down here I don't need. Okay, so assume f double prime is equal to 0, and that is, it exists. Okay, so do a little IE, that is f prime of C is in R and exists. You don't really need that because I'm saying it's 0, but this doesn't work for a DNE case. Okay, let me put this up here. So just put down somewhere. This does not work for a DNE. Just got to put that somewhere. Okay, so it only works when you have a nice smooth portion of the graph. And we'll look at an example where in some cases you can use the second derivative test, in some cases you can't, for the same graph, different critical values. Okay, so assume that, and then we get 1 if f double prime of C is less than 0. What do you think you can say? Okay, so you have this case right here, or well, that was the only case. Okay, so this case f double prime is less than 0. And you have f prime is equal to 0. So what does that tell you about that point? It tells you have a local maximum. Okay, so f double prime of C less than 0, that implies concave down. Okay, so just you can put a little picture here. That's concave down. Then f has a local maximum at C. All right, so you could say, I'll just say like this. So the f of C is a local maximum point. Okay, so similarly to if f double prime of c is greater than 0, that implies concave up. Then f has a local minimum at, it's supposed to be an at c. Okay, in other words, f of c is a local minimum point. Okay. And then 3, if f double prime of c equals 0, the test fails. And use a different method. So you got to do something else. Now, if f prime is a D&E, so f prime is a D&E, then you can't use this anyway. So this does not work for the D&E cases. And I'll just say for f prime. This only works for the smooth portion of the graph. So you could have a graph like this, and I'll give you real examples here next, but you could have a nice graph that does this sort of thing, but then you have a cusp. So here you're going to get, you can apply on these values the second derivative test, but here you cannot, and here you can. Okay, so this, you'll have f prime as D&E. You have to use increasing, decreasing. You have to use the first derivative test. On these guys where it's smooth, you'll get f prime as 0, and you can use the second derivative test. Okay, but we'll look at a bunch of examples to go over all that. Okay, so let me just get rid of that. Okay, so going back to this one, this graph here, I don't want to clutter this, but here and here and here, you will get f prime is 0, f prime, not double prime. You'll get horizontal tangents on all those spots. And so then you may use the second derivative test, and you'll get concave up versus concave down, and that's how you remember. So what I want you to remember is f prime of c, f double prime of c greater than 0 is concave up. Well, that implies a minimum. Okay, so you got to picture what the graph is versus for the concavity, and then say, okay, that has to be a minimum or a maximum. Okay, and then we'll get into, of course, a bunch of examples. So we have a few to do. They take a while. They take quite a while, actually, to go through every little step of these. And I have like 3 of them. Not sure I'll get them done in one video, because I also have kind of an outline of how to graph. And I like to write it out for you and try to teach something, I guess. All right, so that'll be good for this one. On to the next.